we don't need to wait for like the next 15 minutes. I think we can start now. So please.
Do you see my screen?
Yeah, I can see it. It's clear.
Okay, great. Should I start?
Yeah, you can.
Great. Thank you very much. I'm very happy to be giving this talk. I'd like to thank the organizers for organizing this across time zones. And I'm happy to have this opportunity to speak to you all. I'd like to speak to you about setting up the information paradox as a scattering problem. It's somewhat of an old-fashioned way of looking at the information paradox, I suppose, but I think that there's some reason to revisit such an approach. And to some extent, what I will be doing is something that could have been done many years ago. So it's a very field theoretic quantum gravitational approach to the problem. And I hope to convince you that there's an interesting phase in quantum gravity where explicit calculations can be done that may have something interesting to say about the information paradox. This talk is based on a couple of papers that I wrote with a student, Nico Groenenboom and Gerard Hoofd, towards the end of last year. And towards the end, I will also make some comments about some work that is to appear soon. I don't necessarily have to get to the end of my talk if there are questions, comments, criticism. So please feel free to interrupt me whenever, wherever. And if I'm running out of time or whatever, I will find my way to the end. So please feel free to stop me, interrupt me. So I'd like to begin with a whirlwind review of the information paradox itself, or as how Hawking posed it. The premise of the problem is that we think of an existing black hole background. We consider, say, scalar fields propagating on this background. And you see that the lines passing from past infinity, a shell of matter that's collapsing to form a black hole. The wiggly line in the middle, at the top, is the singularity. The slightly thicker lines marked as the event horizon are just the event horizon. And you receive modes of after the black hole starts to evaporate at future infinity at Scri plus. And what Hawking does is to compute to trace these modes received at future infinity all the way back in a free field approximation or a geometric optics approximation. He identifies that the vacuum that's defined on Scri plus is related to the vacuum or the states in Scri minus on past infinity are related by thermal coefficients, Bogoliubov coefficients, and he deduces that there's an information loss from what you send in to what you get out at future infinity. And this is done in free field theory. The essential question that I'd like to ask, or a natural observation, is that especially near the horizon, when interactions are of the order of the size of the horizon, the metric could be fluctuating. There are interactions that come into play with gravitational perturbations. The question is, can these interactions be incorporated into this calculation? Can one compute amplitudes, for instance? And to what extent can we expect to resolve or to understand the information paradox by including gravitational interactions in some consistent way? Of course, one would naively worry already about including interactions, computing loop amplitudes because of non-renormalizability of gravity and so on. I hope that by the end of this talk, I'll convince you that there's a phase in which one can compute amplitudes without necessarily running into these troubles. There's a nice phase in gravity where you can compute these amplitudes. Good. So let me try. I'm stuck with the. Sorry, yeah, so I'm looking at small enough impact parameters. So by that, I mean, we're looking at, think of particles or more of collapsing or colliding with each other in just space-time, in flat space. We think of particles that are interacting gravitationally if they're very far apart. Of course, they essentially don't interact. But even if they're already very far apart, if the interaction energy, the collision energy of the scattering is extremely high, it turns out that there is gravitational interaction that becomes important. And especially if the impact parameter of the collisions is small enough, and I will quantify what I mean by small enough as we go. If the impact parameters are small enough, then we expect that black holes will form. This is just to say that if you collapse matter together, at small enough impact parameters, you will form black holes. And therefore, in this regime of phase space, you cannot ignore gravitational reactions. And the question is whether there's a regime of phase space where you can compute amplitudes. I'm sorry, I can't see a part of my own screen because of the list of participants. Let me try and get out of that. Yeah, sorry. So good. So what I want to do in this talk is to ask, why would you expect such a regime to exist? Well, there are many indications. So one of them is that we expect the information, there's a lot of recent indication that the information problem can be resolved in effective field theory. Think of the island program that has taken off in the last few years. And also an important fact that gravity is sort of special in the sense that quantum effects arise from large momentum transfer, like in quantum field theory, but also from emergent classical scales, like the Schwarzschild radius. So there's probably some expectation that such a regime should already exist. And what I'd like to do in this talk is to define this regime, or to attempt to define this regime in some consistent way in effective field theory. And I hope to compute some, or illustrate how one can compute some amplitudes in this regime. And I hope to convince you that it's clear that there could be a lot more that's done, that can be done. And it sets the stage for me to be able to ask several questions. For instance, what do these amplitudes say about the information paradox? And if you've heard of terminology like the post-Newtonian approximation from flat space gravitational amplitudes, it indicates, what I'm going to display is going to indicate that there's probably a notion of post-black hole approximation. One can ask things like, can one understand scrambling time or page time coming out of these amplitudes? Well, how do I think of asymptotic symmetries, infrared divergences, and so on? That's a sort of a rough overview of what I want to head to. And here's a plan for the talk. I'll first start with large impact parameters to review what is very well known as the flat space iconal phase of quantum gravity. And then I will move to smaller impact parameters, where I define what I'll call a black hole iconal phase. And then I'll end with some comments on various aspects that I just alluded to. So let me start with reviewing what the large impact parameter space is, flat space iconal phases of quantum gravity. But before that, based on just a quick overview, I'd like to pause for a couple of seconds to see if there are any questions already. Okay, if not, let me continue. So large impact parameters, what do I mean by that? Throughout the talk, I'll label the impact parameter to be a parameter B with the symbol B, and think of a collision or scattering of particles with some center of mass energy S, the Mandelstam variable S. When they're interacting gravitationally, there's a natural length scale that arises from this interaction, which is g Newton times the square root of S. So every time I say large impact parameters, I mean that the impact parameter is larger than any other scale in the problem. And the two scales in the problem are Planck length and g Newton times the square root of S. So the length scale associated to the scattering itself. So if impact parameters are very large, as long the center of mass energy of these collisions could still be very high. So for example, consider this red particle that's drawn on the screens to the left of your screen, traveling at the speed of light. And think of a test particle that's traveling in the orthogonal null direction, that's drawn in green. The energy associated to this collision could be 1 over g Newton times the test mass of the particles. So if these are actually light-like particles, this energy could be very high. And even though the particles are very small and the impact parameters are very large. Nevertheless, because of this high center of mass energy, one cannot ignore gravitational back reaction. And it's very nice. One can actually incorporate this already at the classical level in a very nice way. And it's what is known as the Eichelberg-Sechsel shock wave. So what happens in this picture is that the green test particle gets kicked along the momentum of the red particle, and then it continues propagation. So whenever it encounters a shock wave, you get kicked a little bit. And this is work done by a lot of authors that I list here, and there's many more people who contributed to such an understanding in various ways. So one can write down the shift in geodesics as a classical solution to Einstein's equations. So this is a classical nonlinear solution to Einstein's equation that one can write down. So this is the back reaction of the red particle on the space-time, which is a shock wave. Interestingly, this can also be seen in an effective field theoretic setting. And here's how that works. That's called the flat space iconal regime. So let's consider perturbative quantum gravity in the background field method. So I will expand the metric. Sorry, is there a question? No. So let's think of the background field method where I'm perturbing the metric to be flat space plus perturbations. And there are interactions in this theory that are generated by the coupling of the graviton to the stress tensor associated to, say, a minimally coupled scalar field. And if you focus on the S much bigger than T regime of phase space, so S and T are the Mandelstam variables, and now consider diagrams that are leading in center of mass energies that are much greater than Planck mass. It turns out that the dominant diagrams are what are called the ladder diagrams, which are drawn at the bottom of your screen. So the one to the far left is a tree level 2 to 2 amplitude or 2 to 2 Feynman diagram. The one after that is the one loop. The one after that is also the one loop. But remember that I'm only including 3-point vertices which has a single graviton leg talking to 2 scalar legs. So the gravitons in the third diagram do not self-interact. You could, of course, incorporate all the higher order corrections to graviton self-interactions and so on. The last diagram that you see is a 2-loop diagram. There are 6 of those with all possible attachments and so on. Remarkably enough, one can calculate these amplitudes explicitly at all loops and then resum all of them. And one can write down a very neat amplitude, which looks like so. It's an explicit expression that one can write down. So as you see, all the parameters are essentially what I've already mentioned. So S is the Mandelstam variable, is center of mass energy. G Newton is just a coupling constant. T is a momentum transfer. Sorry, it's a momentum transfer. There's this parameter mu, which has to be introduced because there are infrared divergences in these amplitudes, and there's a regulator that's necessary, which is like, you can think of it like a graviton mass. Where does this come from? It just comes from the part of the diagrams where the virtual gravitons go on shell. So you have an infrared divergence coming from the propagator of the graviton. It's interesting that one can actually write down such an amplitude explicitly, and this is called the flat space iconal regime. However, of course, in gravitational scattering, we know there must be black holes. So where are they? It turns out that they begin to appear when impact parameters are reduced in size as they begin to be comparable to G Newton times square root of S. And the way this was noticed was that these iconal amplitudes receive corrections which begin to diverge as you take the impact parameter to be smaller and smaller. And one can interpret this as an intermediate state that's being produced as you reduce impact parameters. This is something that I mentioned earlier. It's an indication that gravity is sort of special, that quantum effects arise due to emergent scales. And in this case, the Schwarzschild radius emerges as the scale associated to the scattering, which is G Newton times square root of S, when the impact parameters compete with that radius, with that length scale, sorry. So instead of, so what one could, of course, correct this picture. And this was done in a series of very famous papers by Amati, Cioffoloni, Veneziano, and a lot of others thereafter. And the natural thing that was done was to incorporate stringy corrections. So when you include those, you have 3 natural length scales. So one is the Schwarzschild radius associated to the collision, which is G Newton times square root of S. And we take this to be much bigger than Planck size, the L Planck, such that we are in semi-classical gravity. And there's, of course, alpha prime. So the square root of alpha prime, which is the string length. And we want to take the string length to also be much bigger than the Planck length. And that's true when G string is very small. So there are 3 scales in this problem now. There's the impact parameter at which collisions happen, the Schwarzschild radius associated to the scattering itself, and the string length. Now one can consider different regimes of parameter space. So the first one is the flat space iconal that I just mentioned, which is when the impact parameter is much bigger than any other scale. So it's much bigger than Planck length, it's much bigger than the Schwarzschild radius, it's much bigger than the string length. And there are natural corrections that one can incorporate to this flat space iconal, which would give you corrections to the diagrams that I just showed you. And these would be perturbative in Schwarzschild radius over impact parameter or string length over impact parameter. As a flash, for example, the classical corrections that arise from the Schwarzschild radius over impact parameter are also called could start to look like what are called the H diagram. So they arise from 3-point graviton interactions that are in the green circle. And there are vertex corrections that give you quantum corrections associated to some UV length scale. There's the next regime, for instance, is when you take the string length to be greater than the Schwarzschild radius. So this is where before you hit classical black hole production, stringy effects start to dominate. So as you reduce your impact parameters, your string length, you hit string length before you hit the Schwarzschild radius associated to your scattering. And it was observed that in this case, well, it's constructed such that stringy effects dominate classical black hole production. And if you start to take the string length to approach the Schwarzschild radius, people observe that in these papers that are quoted above, people observe that there's a black hole-like behavior in the sense that the final momenta in your out state are inversely proportional to the size of the horizon or the size of the length scale associated with scattering. What's interesting to note is that in this regime, one can consistently study what's called the black hole string transition, which is, as you see on the expression to the far left, the bottom left of your screen, you can take the string, the Schwarzschild radius over the string length to be very large or very small, depending on how you tune G string. So if you take G string to be very weak, you can be in the regime where the Schwarzschild radius is very small. If you take strong coupling regime, then you're in the opposite regime. So both regimes can be thought of in some consistent way. Finally, if the impact parameters are smaller or comparable to the size of the emergent scale, this is where we expect to have classical black hole production. In some sense, this is where we say that there are strong gravitational effects when you think of scattering on flat space. This is what I want to focus on. This is a regime that's often thought to be very hard to capture. And I want to convince you that there's a certain sense in which important aspects of this regime can still be captured in effective field theory. And once you're able to say something in this regime, one can of course ask similar questions about the black hole string transition again by tuning G string, as I said before. So as a recap, I'm now interested in a regime where impact parameters are much bigger than Planck length because I want to stay in semi-classical gravity. And yet I want to be in regimes where impact parameters are comparable to the emergent scale or to some Schwarzschild radius. And the phase in which amplitudes in this regime can be computed turns out to be the regime where the second equality should be inverted. It's where square root of S times M black hole is much bigger than M Planck squared. Remember that in flat space, the impact parameter was the greatest length scale, and the collision energies were much bigger than Planckian. So there were trans-Planckian collisions at large impact parameters. Now we want to have, because of the emergent scale, which is the black hole mass, it's very easy to satisfy this regime because you have, instead of S being much bigger than trans-Planckian, there's a large scale. So you could have energies which are very low in collisions and yet satisfy this regime. I'll show you how this regime appears, but this is roughly the focus of what I'm going to talk about next. And this is where I want to head to smaller impact parameters and what I will call the black hole iconal phase. Let me pause here for a few seconds to see if there are any questions about what I've said so far.
Can you please go back to your previous slide?
Yes. This one?
So you have the product of black hole mass and energy much smaller than the Planck scale.
Sorry, much bigger. I said it wrong. I thought I needed a correction, but it should be much bigger than the Planck mass squared.
But that's what you have written.
Yes, I thought I hadn't corrected it.
No, okay, right. I just wanted to clarify that.
Yeah.
And now I understand. Yeah.
Okay.
Thank you.
Yes. Okay. Any other questions? Okay. In that case, let me move on. So a couple of facts that I want to appeal to. This, what I'm about to say is not essential, but it's an interesting observation. It's the following. If you have infalling matter, so here's a Penrose diagram of null matter that's collapsing to form a black hole. If you have infalling matter that's falling radially inwards, we know that an apparent horizon already forms before an event horizon, so to say. In a dynamical collapse, an event horizon is something that's an approximate notion that arises later. But an apparent horizon already forms as matter is falling in. So if you think of matter that's sort of falling in towards the end of the collapse, that's where the apparent horizon begins to agree with what we call the event horizon, and they're approximately the same. So already towards the final stages of the collapse, matter that's forming the black hole essentially appears to be falling into something that's already already looks like an existing black hole. So of course, modes that if you throw in an extra particle much after the black hole is formed, it just looks like it's falling into a black hole that's already formed. But that's also approximately true already towards the end of the collapse. So in some sense, there's some approximate sense in which one can argue that by studying fields propagating on a black hole spacetime, you're already capturing at least some part of the collapsing problem, which is in some sense what Hawking has already done. It's sort of a justification for why one may want to study fields moving on an existing black hole background, while still keeping in mind that it may have something to say about a collapsing problem. If one doesn't appreciate this, one can still ignore the collapsing problem and just think of everything that I'm going to say later on as just fields propagating on an existing black hole background. Good. So I want to define what I will call the black hole iconal phase. Just as in the flat space iconal, I want to work in the background field method, where instead of perturbing around flat space, I now want to perturb around a background which is a Schwarzschild metric. And just like before, I want to think of interactions that are generated by a 3-point vertex, which is a graviton coupled to the stress tensor, and the familiar covariant gauge that one imposes, which is necessary when you have gauge theories. It turns out to couple different spherical harmonics, all the partial waves. And because the background is a little bit more complicated, the graviton propagator is not known analytically everywhere in space-time. So that's very difficult to compute. So it makes the previous calculation very hard to replicate. However, turns out that this is a very nice gauge that was invented by Regge and Wheeler in 1957 in a beautiful paper, which fits the bill. In this gauge, you can write down the graviton. You can split it into odd and even parity modes, which I schematically wrote in the expression to the right. The block diagonal part is the even parity graviton. There are 10 degrees of freedom in the metric. You gauge fix to arrive at 6 off-shell physical degrees of freedom. And here you see that in the even parity mode, there's HAB, which is a 2x2 symmetric tensor. So there's 3 degrees of freedom there. And K is a scalar that's on the transverse sphere. So that makes it 4. And there are 2 degrees of freedom in the odd parity graviton mode. So this is Regge-Wheeler gauge. If you plug this gauge into your background field method and you perturb your action to quadratic order, for instance, it turns out that in this nice gauge, all the tensorial harmonics associated to expanding the metric tensor in spherical harmonics reduce to regular spherical harmonics. And it also turns out that odd and even parity gravitons decouple. Moreover, if one is working with low transverse momenta, it implies that one can check explicitly, and we've done this in this paper with Nico, that the odd parity graviton does not contribute to the amplitudes that I'm about to discuss. That's not obvious, it's just a tedious calculation one has to do. So I'm looking at the perturbed action now on about the Schwarzschild background. And now I want to look at interactions that are generated by this 3-point function, this 3-point vertex. Of course, naively, we think of all the 3-point vertices. If I expanded in partial waves, I would have Klebsch-Gordan coefficients that couple all my partial waves that are generated. The coupling is generated by interactions. At quadratic order, as I said, all the partial waves decouple, but interactions spoil that. But if you now think of a large black hole with 2 particles interacting on top of this horizon, on an existing black hole background. Spherical symmetry is approximately preserved. We wouldn't think that an interaction with sufficiently low enough energies compared to the size of the black hole itself would destroy the spherical symmetry of the solution. So you could approximate it, and that's what I will do in the rest of this talk. This is not necessary, meaning that one could keep track of all the Klebsch-Gordon coefficients, and most of what I'm going to say is going to carry through, but it's just easier to write simpler expressions when you approximate this to all the interactions to be spherically symmetric. So what I've done on the right-hand side of your screen is at every interaction, every 3-point vertex, I've drawn the scalar field, the two scalar legs, one with a solid line, one with a dashed line. I just want to keep the dashed line as something that's spherically fixed. So something that's at a fixed partial wave, so that I can essentially decouple all the coupled partial waves, assuming that there's approximate spherical symmetry. As I said, this is not strictly necessary. It's just a convenient thing that one can do, which holds true to pretty good approximation. Another way of saying it is that at quadratic order, which is what Hawking worked at, all the partial waves decouple. So I'm trying to work through the interactions while preserving approximate spherical symmetry. So with everything that I said so far, here's some naive definition of a black hole iconal phase. It's the following. Firstly, it was noticed that longitudinal and transverse effects, there's a huge separation in scales. This was first noticed by the Verlinde brothers in 1991 in a very nice paper. This is a statement that partial waves do not mix, and it has the consequence that transverse momenta in my scattering amplitudes can be ignored. Second, I'm interested in impact parameters that are comparable or smaller than the Schwarzschild radius and yet bigger than the Planck length. This means that I can consider scattering of particles near the horizon. Because the particles are confined to the size of the sphere, it implies that the impact parameters are necessarily of the order of the Schwarzschild radius or smaller. And I just want to stay away from the regime where Planckian effects take place, because then I don't know what to do. As I said, the emergent scale the scale associated with the size of the black hole allows for very low collision energies. So unlike in the flat space iconal, collision energies are not necessarily trans-Planckian. The formula that I wrote all the way at the start, which was square root of S times M black hole is much bigger than Planck mass square. I've rewritten it here, which is to say square root of S is much bigger than gamma times M Planck, where gamma is M Planck over M black hole. The reason for writing it in this form, to introduce this new dimensionless parameter gamma, is it turns out that gamma governs the coupling constant or the interaction of my vertices. Good. So with everything that I've said so far, one can brute force compute the Feynman rules on the horizon, so in the near horizon regime. Now, if you look, and I'm working in partial wave basis, so I've integrated out the sphere, and I'm now left with a effective two-dimensional problem. So on the left top, you see the Feynman rules for the scalar field. The solid line has a familiar propagator for the scalar field. Lambda here is L squared plus L plus 1, which is the partial wave in question. Sorry. And the dashed line, as I said, is I've just left it to be fixed in the L equals 0 mode. So that has lambda equals 1. And finally, it's the graviton propagator. As I said, in general, on the Schwarzschild background, it's very difficult to write down. There's no known analytic form for the propagator for the Schwarzschild metric. However, with the approximations that I've made so far and working in the near horizon regime, one can explicitly compute the propagator, invert the kinetic operator. It's a tedious calculation, and you can find all the details in my paper with Nico. And the propagator has this form that you see on the right top of your screen. So it's interesting to look at this to understand various terms that appear in this. So the first two terms that appear in the brackets are momentum independent, and they look like they're just flat space. And this is because the near horizon regime of the black hole is essentially conformally flat. So there's some piece which looks like flat space propagators, but notice that there's a prefactor which has the emergent scale, or which has the infrared scale, which is the Schwarzschild radius. The third term in the brackets contains all the momentum dependent pieces. And there are, of course, expected UV divergences in this. So I've not solved any great problems with non-renormalizability and so on. if you take K to be very large, you run into divergences. However, because of this emergent scale, because of the infrared scale of the Schwarzschild radius, there's an effective two-dimensional mass for the graviton in the near horizon region. So that what I mean by that is that there's no singularity if you put K equals 0 in the propagator. There's no infrared divergence that appears. Notice that this is not a graviton mass that's been introduced. This is just an artifact of the reduction to 2D. The four-dimensional graviton is just massless. I haven't done anything magical. And as I said, the 3-point vertex has a coupling constant, which is gamma, m Planck over m black hole. One of the nice features of this is that when one computes amplitudes in the near horizon region, amplitudes are naturally infrared regulated because of the infrared scale associated to the black hole. There are some gauge subtleties for the S wave and the L equals 1 mode for the graviton. And there's also some it's easy to see, for example, that if you take lambda, if you take L equals 0, the momentum dependent piece in the propagator flips sign compared to the S wave and the higher L modes because of the lambda minus 3 in the denominator. Moreover, when L equals 1, there's a singularity. And this is just an indication that there's some additional gauge redundancy in these two modes. They can be consistently taken into account. One introduces Faddeev-Popov of ghosts. This can be done. And it's also written down. There's some exposition of this in a nice paper by Renata Kalos and Adel Rehman earlier this year. It will turn out, as we go towards the end, that all the amplitudes that I'm computing, the 2-to-2 amplitudes that are analogous to the flat space iconal, will turn out to project to the soft sector of the graviton. So the momentum dependent pieces will not contribute. And it's only the leading order piece, it's the momentum independent soft factor that contributes to the amplitudes. It's an outcome of the calculation. And in some sense, it's an outcome of the iconal phase. Excuse me. So what I'm first interested in is computing 2-to-2 amplitudes in this black hole iconal. There are 3 scales again in this problem, which is the Planck mass, the black hole mass, and the center of mass energy of the collision. We're going to work perturbatively in this iconal regime, which is to say that energy is much bigger, the collision energy is much bigger than gamma times m Planck. This will have the consequence that only soft diagrams contribute. There's no momentum exchange, so to say. And we will sum over infinitely many Feynman diagrams, the same form of ladder diagrams, which is to say that will be non-perturbative or perturbatively exact in gamma. So the 2-to-2 diagrams at one loop, they just look like the diagrams in flat space. However, remember that I've made the approximate spherical symmetry assumption here. So you see that at every vertex, there's a solid line and a dashed line. So the solid line, at one loop, the solid line stays on top. So angular momentum is conserved at the top of the Feynman diagram. Whereas at 2 loop, you see that the solid line goes to the bottom. So the angular momentum is transferred across the graviton. But as before, as in flat space, the mathematical steps are very similar because of the conformal flatness of the horizon. One can explicitly write down all these ladder diagrams, compute these amplitudes. The general amplitude is again written in terms of some single function chi. And they can be explicitly evaluated. And as you see, the soft limit is enforced upon us. So there's a delta function when you integrate over all the momenta. So one is projected into the soft sector, and the iconal function is written in terms of the Schwarzschild radius, gamma, the center of mass energy, S, the Mandelstam variable S, and the partial wave in question. However, notice that the Schwarzschild radius and gamma appear in a combination such that the infrared scale disappears from the amplitude. So one's just left with 8 pi g Newton times S. In contrast to the flat space iconal, if one were to do a similar calculation in flat space, the g Newton times S dependence remains the same. However, it's the large angular momentum modes that dominate the flat space iconal, whereas in the Schwarzschild, in the black hole iconal, it's the low angular momentum modes that seem to dominate. That's a physically contrasting difference between the two regimes. So this is a general loop amplitude, as I said. All these diagrams can be neatly resummed, and one obtains a beautiful exponential. So they exponentiate. It's a theme. It's a very natural thing that happens in any iconal approximation, also in quantum field theory. So the diagrams exponentiate, and one can write down the complete amplitude. Again, one can relate this amplitude to a classical nonlinear solution to Einstein's equations. If you're familiar with the Stanford Schenker paper in 2014, they've done something similar. However, there's an important difference, which is that this classical metric, I have to say, is the Dreyerhof shock wave. So the Eichelberg-Sechser shock wave is a shock wave on flat space. The Dreyerhof shock wave is a shock wave on a black hole background. So very nicely, one recovers this amplitude from the shock wave as well. However, there's an important difference, which is this factor of 2 that I've circled in the final amplitude. If one does the calculation on shell, meaning that one computes this amplitude using the shock wave metric, one obtains an L squared plus L plus 1 in the denominator. So at L equals 0, it's the dominant S wave mode, it's a factor of 2 that's different. And one may be puzzled because in the flat space case, there was no difference. The amplitudes exactly match. As it turns out, well, already in quantum field theory, we know that if you have tree-level amplitudes, the virtual particles that are exchanged can be off-shell configurations. Now, it's only the external legs that are on shell. As it turns out, the amplitude in flat space only contains on-shell virtual legs, whereas in the black hole background, there are off-shell contributions that also contribute. But remarkably enough, they only renormalize this little factor instead of changing the form of the amplitude. And we've checked explicitly that if you demand that the virtual gravitons that are exchanged are also on shell, that they satisfy Einstein's equation of motion, then you reproduce exactly what you expect from the shock wave, which is L squared plus L plus 1. So there's some interesting off-shell features that appear in the loops or in the virtual particles in this amplitude. So that's so much for 2 to 2 amplitudes in the black hole iconal phase. I move on to make some comments before I finish. Are there any questions here? Okay.
I just wanted to make sure you're saying
Yes.
that the classical calculation with the Dreyerhof shock wave actually does not reproduce the summed iconal result?
That's right. There's this intriguing factor that's different. And it's a neat factor of 2. I don't have a very good interpretation of this factor. There's probably a good interpretation. I just don't know of it yet. What I've explicitly checked with the student, with Nico, is that the extra factor of 2 comes from virtual gravitons that are exchanged in these amplitudes, which are off shell, whereas the Dreyerhof shock wave is an on shell solution. Therefore, there are no off shell contributions to this amplitude from the shock wave.
I see.
Seems to be a characteristic difference compared to the flat space calculation.
Is there any difference if you were considering not asymptotically flat Schwarzschild, but ADS Schwarzschild?
We haven't done the calculation, but it can very easily be done, because the only thing that would change is a term in the graviton propagator, which arises from the contact term of the cosmological constant.
Right.
But because everything is projected into the soft sector, this will probably be a constant shift in one of the parameters in the propagator. Therefore, I don't expect the physics or the interpretation that follows to change dramatically. But I haven't done the explicit calculation. Something that we're trying to do.
Thank you.
Are there any other questions? Okay, if not, let me make some comments about various aspects that may be of interest to a different audience. So the first thing is that nobody told me that the outgoing particles from the black hole. If I throw two particles into the black hole, they exchange some gravitons. Nobody told me that only two particles must come out. In fact, that's probably an exponentially suppressed amplitude, the one that I just computed. It has a nice classical regime because of the iconal resummation. But in general, one would expect many out states to show up. So it's of interest to compute 2 to n amplitudes. So here's an example of a 2 to n amplitude. This is a tree level diagram. First thing is that unlike in the 2 to 2 amplitude, momentum transfer starts to become important. For momentum conservation, all the outgoing modes should have the same momentum as the ingoing modes. Therefore, the larger n is, the softer the outgoing external particles are. So the more likely that you want to see these as Hawking radiation, if you will. And for different values of n, there are many different out states that are possible. At tree level, all diagrams are easily calculable. There are no integrals to do. As it turns out, that one can extend this to loops. So imagine I wanted to make a one loop calculation. I could insert a graviton between any of the two legs here. So there's n such possibilities, or actually n, the number of possibility scales with n. And if I wanted to make a two loop diagram, then I could put in any two combinations. So it turns out that there's a natural exponentiation that arises from the 2 to n amplitudes. And we're almost done with writing this up. And it turns out that one can actually resum the iconal diagrams again in 2 to n amplitudes. It looks like one is able to write down an all loop result for 2 to n amplitudes too. This is of particular interest for many reasons. One is that this n may have something to do with the black hole entropy. And the other is that we know that the 2 to 2 amplitudes have had a serious impact on quantum chaos and studies of quantum chaos, with the Lyapunov exponent that shows up in the out of time order 4-point functions, for example. So one might wonder, if I consider 2 to 4 amplitudes, so that's like a 6-point function or an 8-point function, a general n-point function, if there are additional exponents that show up, or if there are any other exponents that in some sense capture higher moments. This would be very interesting to understand. So in some sense, one may want to think of this as an n-point chaos bound that may show up. I don't know if such a thing shows up yet, but it's a very nice possibility that's worth exploring. And this formalism and this phase of the theory allows us to possibly calculate this explicitly. An additional interesting feature of computing 2 to n amplitudes is the following. Given any scattering amplitude, there's a natural time scale that one can associate to it, which defines for you the time scale of the scattering process itself. So this is to say that if I have some potential and some scattering process that's happening, how long do I have to wait in this potential before I start to receive information of the outgoing states? So how long does the scattering roughly take, very morally speaking? This is called the Wigner's time delay. And it turns out that if you compute Wigner's time delay for 2 to 2 amplitudes, it's the elastic 2 to 2 amplitude, that gives you scrambling time. So it's to say that if I throw two particles in the near horizon region, they take roughly scrambling time to scramble across the horizon before some outgoing modes capture any of the ingoing information. However, if one computes 2 to n amplitudes and resums the iconal, it looks like the time delay associated to the Wigner's time delay associated to such a process scales as m cube, m black hole cube, which is very indicative of page time. So it looks like this phase actually may capture dynamics over long enough time scales to say something about unitarity, but that you will only observe unitarity, meaning the scattering process completes, so to say, only after you wait long enough, which is page time, which is something that we would have expected anyway. There seems to be a natural phase in the theory to get it out of a very honest calculation, so to say. So much for 2 to n amplitudes. Perhaps I'll, so I could say something about this. So if you think of another interesting observation is that the Minkowski diamond, as I've drawn it here, is such that spheres on the right half of the diamond are antipodes of the spheres on the left half. So you have, each point is a half sphere, so to say. So if you have a black hole in the middle and you have 2 to 2 amplitudes that are traveling along light-like directions, the two outgoing modes are essentially appearing from antipodal points, or they reach antipodal points on future infinity. So that's to say that there's probably a natural antipodal identification on the horizon itself. and it's a condition on the horizon, not at spatial infinity. This is something that's an interesting proposition that was made by Hooft, and this it's something that needs to be looked into. There's probably much more to be said about it, but it's an observation that can be made. And it seems to be important for unitarity. So in the sense that if I only look at one of the outgoing particles, of course, I don't recover all my information of the scattering process. There's something to be said about asymptotic symmetries. One thing that we've learned about studying symmetries at null boundaries, null infinities, for instance, is that if you take all the conservation laws into account properly, then there are no IR divergences. However, we saw that in the flat space iconal, there are infrared divergences in the iconal phase. So that's probably to say that there are some conservation laws associated symmetries near future infinity that are not being appropriately taken into account in the flat space iconal. However, in the black hole iconal, we saw that there are no infrared divergences. They're naturally regulated by the infrared scale. But what are the symmetries? These are probably related to near horizon analogs of BMS, as we saw in, for example, Shaheen Jabbari's talk. Another way to say this is to say that these shock waves or these particles that are falling into the black hole, they imprint supercharges on the horizon. This was already observed by Hawking, Perry, and Strominger a few years ago. And they probably imprint certain conserved charges, and the antipodal identification may be a statement about a boundary condition on the bifurcation sphere, for example, of a two-sided black hole. There's some work in progress, but there's some concrete statements that one may be able to make about asymptotic symmetries with these amplitudes considered. This probably is it's an interesting viewpoint on how to understand near horizon symmetries and how they relate to scattering amplitudes in the near horizon region that I've just described. Another interesting, perhaps, application of this entire formalism, in the flat space iconal, there's a natural post-Minkowskian approximation where one includes corrections away from the iconal phase. And in fact, there's an effective one-body formulation that's down to very beautiful work by Thibaut Damour and collaborators, which essentially tries to understand the in-spiral phase of two black holes spiraling inwards to collapse and merge. And what's done is usually to treat these two black holes that are spiraling in, to be treating them as point-like particles with heavy mass. And the in-spiral phase is somehow governed by exchange of graviton propagators between these two particles, heavy particles. And this seems to be surprisingly good approximation to certain features of gravitational waves that we see from mergers in the in-spiral phase. And as I said, it's natural to think of, and the graviton propagator that's used there is the flat space graviton propagator. It's now that with the contrast with the flat space, as I've shown you, the black hole iconal seems to be dominated by the low angular momentum modes. So it's very likely that in the merger phase, which seems to be very difficult to capture, one is forced to use, one may get a better approximation of the merger phase by using the black hole propagator, graviton propagator. And in the same sense, one may have some notion of a post-black hole approximation. This is a very interesting application that seems to be a natural consequence of how the amplitudes look and what the difference in the physics seems to be between the flat space and black hole iconal. It's something that's probably waiting to be explored in very concrete ways. So finally, let me conclude, and towards the end of my talk. What should you take away from everything that I've said so far? The first one is that there seems to be a remarkable new phase of quantum gravity that seems to capture black hole evolution. Presumably, the information paradox can be addressed in this phase, especially if one computes 2 to n amplitudes and is able to compute loop diagrams and so on. And there's every indication now with some work that I'm about to finish that this is possible. Importantly, there's no UV completion necessary here because I've worked in effective field theory with essentially everything that I'm allowed to do within quantum field theory rules, so to say. And there are exponentially suppressed corrections that arise from various amplitudes, but there seem to be many such, which presumably say something about unitarity. And one can easily extend everything that I've said to include stringy corrections and treat the black hole string transition. There are several aspects analogous to the flat space iconal waiting to be discovered. All these beautiful papers by Amati, Cefaloni, and Veneziano they have a very concrete understanding of all the corrections that arise away from the iconal phase and what they physically represent. And all of those presumably have very interesting similar physics associated to corrections away from the black hole iconal. And it's very interesting, as I just said, to understand what a post-black hole approximation might look like and what physics is captured here. It's something that I haven't discussed in this talk because I haven't had enough time, but there's a notion of gravitational echoes that arise from this entire procedure with this entire near horizon scattering. The way to think of it is the following. There's a classical potential barrier that's a little bit further away from the horizon, which gives you your quasi-normal modes, if you will. Because of this near horizon scattering, there are modes that are emerging from the horizon, but they hit the gravitational potential, the classical potential barrier. Some of them leak out towards infinity, but some of them go back. So they scatter back and forth, and they give out gravitational echoes that leak out to infinity. And in this model, these echoes, well, this is not really a model because I just used Einstein's theory, coupled minimally to a scalar field. So there are no new parameters that I've introduced, and they seem to predict gravitational echoes coming from black hole horizon dynamics. It'll be very interesting to compare these with other models which have tunable parameters that predict echoes with exotic compact objects, for instance. I wrote a paper with Panos Betsios and Olga Papadolaki towards the end of last year, discussing some of these aspects, but I haven't had much more time to discuss this here. Finally, there are many interesting things that can be improved upon, the things that one can work on, building on what I've presented so far. One of them is that there's a very natural, effective formalism bottom up. So if you will, to understand ultraviolet physics by including perturbatively corrections away from the black hole iconal phase. For example, the transfer scalar mode K, which was in my metric perturbations, did not contribute at all to what I said so far. This runs into some of the diagrams. They just happen to be subleading in all the calculations that I've done so far. But one can ask questions about subleading corrections, which are still calculable in the effective theory, and wonder if they give you any hints or directions towards ultraviolet physics. All extensions of flat space iconal regime can be repeated with these tools, as I said, when we want to understand how to get an entropic scaling from these amplitudes. One can include standard model correction fields to repeat everything that I've said instead of scalar fields to all the standard model fields. The calculations just follow in a relatively straightforward manner. I've only included the 3-point vertex. Of course, there's an infinite series of higher order interactions. One may expect them to be subleading, especially in the soft sector, but this is something that's important to understand, and they can be, in the effective theory, order by order incorporated to compute amplitudes. This is a perfect playground for small black holes in ADS-CFT on which there's very little literature. And one may want to understand what a CFT interpretation of what I'm doing is. Another very interesting aspect of this amplitude is that given some bulk dynamics, one can try to understand energy-energy correlations or event shapes at future null and null boundaries. So these are non-local correlations in the field theory at future null infinity. That's an interesting thing to compute and understand how one may reformulate Hawking's paradox in terms of energy correlations on a null, in terms of light ray operators, for example. Everything that I've discussed so far revolved around the important fact that there's an infrared scale associated to certain gravitational backgrounds, namely the Schwarzschild radius in this talk. Of course, there's another very interesting infrared scale, which is the Hubble radius of the universe. And so there's probably a cosmological iconal that's waiting to be discovered, although defining asymptotic states there is probably a little bit more tricky than in asymptotically flat space. I've discussed only scattering matrix elements, but one may want to understand experience of an infalling observer. And given that there is an effective theory that seems to describe important physics of near horizon dynamics, maybe some way of putting in an in formalism into this theory may be important or helpful in understanding the experience of an infalling observer, for example, the firewall problem and so on, in a very calculable manner. I hope that I've conveyed some of my enthusiasm of this topic to you. Thank you for your patience and for attending this talk. I'm happy to take any questions or comments or criticism. Thank you very much.
Thank you very much for your talk. Any more questions? Seems that everything is clear. So any more questions again before we move to the next talk? Actually, we are a bit ahead of time. about 20 minutes ahead of time. So in that case, let's thank Nava again for his nice talk. Thank you very much.
Thank you.
Okay, I guess we can move to the next one now. Gustavo Turiachi, I think he is in the list now.
Hi, yes.
Yeah.